All right, so we're going to do a straight line approximation Bode plot. Now again, here's a transfer function, 200,000 s plus 1, here's an s plus 10, and s squared plus 80s plus 100 squared, whatever that is, 10,000. So here it's been factored, and it would be very easy in MATLAB to go in and everywhere you see s, put in I omega and get magnitude and phase as a function of omega, and you could plot that out. We're going to do this by hand using the straight line approximations on a Bode plot. All right. So there's a process to doing this. All right. If you're going to do this, you need to follow the steps I'm showing you. And so the first step is to get everything in the unity static gain form. And that we're going to see right here. All right. So what am I going to do here? Here I got a 10,000. I'm going to divide this whole system by 100 squared. Okay. This one by 10. This is in unity static gain form. Don't have to do anything. So when you look, I got 10,000 here and a factor of 10 here. That's 100,000. So here I factor out the 10,000. So I have s on 100 squared. So that's effectively 10,000. I divide by 10,000 here. I get 0.008 s. Here I divide this 10 out. I get s on 10 plus 1. So at the lowest, for the power s to the 0, I want 1s everywhere. So I'm putting all my gain right here. Then this is just the unity static gain 0, a unity static gain pole, and then a unity static gain second order pole. Okay, so this now fits all of those things we did in the previous couple of lectures for a straight line approximation. So what do we do now? Now we're going to go through and we're going to plot the gain, this 0, that pole, individually, and then we add them up. So step 1, always get everything in unity static gain form as we have here, and then just lump all the gain together. All right, and then as I said, plot each factor, add them all up. So let's make that start to happen. So looking just at the gain side for now. All right. So here we have the gain. 200,000 over 100,000 is just 2. So the K1, 20 log of 2 is 6 dB. So here this is supposed to be at, see, 0, 20. So here we are at 6 dB. This is just the gain term by itself. All right. Then I'm going to have the 0. This 0, this is called the break frequency. When we form this, so kind of where the pole is, so this pole's at -1, so here's this 1. When you've put in unity static gain form for a 0 or a pole, we call this one the break frequency. So what does it mean? Well, we're going along the horizontal. We hit one radian per second, and we break off at plus 20 dB per decade because there's just one power of s. If this was s over 1 plus 1 squared, then we'd actually go up at 40 dB per decade because there's 2 of them. Okay, but there's just one. Then we go down and we have this s on 10. It's a pole. So that means here's the break frequency, which is like a natural frequency. Function is sort of the same way. So we get over the 10 radians per second. We'll break here, and we're going to drop at 20 dB per decade because there's one power of s. Now here we have the natural frequency, which is, this is omega n squared here, but there's the squared, so here's omega n. So at 100 radians per second, we go along, and then we drop, because there's 2 powers of s, at 40 decibels per decade. So if you look, we get to 1,000, we're down 40. If you got to 10,000, we'd be down to 80, minus 80 decibels. All right? So for every power, we drop or raise at 20 dB per decade. Okay? And then at the effective natural frequencies, which we have an actual one right here, at 100, then at 10, and at 1. We go up 20, down 40. Now let's look at the frequency side. All right. This gain, it's a positive number, so its phase is 0. There's nothing to plot. Here we have the 0. Okay, this acts like a natural frequency. Okay, so at 1 radian per second, we will have added 45 degrees, half the phase. So we go 1/10 of that, that'd be 0.1. And then we go 2 decades, that'd be 10. And we gain 90 degrees. So when we hit 0.1, we go up at 45 degrees per decade, decade 1, decade 2, level off. Now here, the break frequency we had is 10. That acts like the natural frequency. And at that frequency for 10, we lose half the phase, so 45. So we go 1 decade in front at 1. Here we are at minus 45. So this is like a natural frequency, very much like one. And then we go another decade, we lose our 90. 1 power of s causes a 90-degree shift over 2 decades. And then it levels off. All right? And let's see. Then the last piece we have here is that omega n equal to 100. That's right here. Okay. We go 1 decade in front. We start to drop at 90 degrees per decade. And then when we do that over 2 decades, here's 1,000. And I didn't quite finish this, so I'll do that right now. And there we have it. So now we have this one. Here's the natural frequency-ish of this thing. At 1 radian per second, we go a decade down, a decade above, plus 90. All right, here we are for this one. We have half the frequency at 10, so it loses 90. And then at 100, over 2 decades, we drop 180. All right, now the nice thing about this is, in these semi-log plots, everything adds. The decibels add, the degrees add. All right, so now we just take this and we add them up. Okay, so let's just look at one at a time. So we start here, 0 plus 6 is 6. So 0 dB. When we get to 1, we start going up at 20 dB per decade. But at 10, we start going down at 20 dB per decade. So that's a 20 up, that's a 20 down. That levels off forever. From here on out, this and that cancel. When we get to 100, though, now here comes another 40 dB per decade drop. So we started at 6, go up by 20 dB per decade from 1 to 10, level off from 10 to 100, and then we drop. And we're dropping at minus 40 dB per decade from here on out. All done. There's a straight line approximation. Okay, now we do the phase. The gain had phase of 0, so that was irrelevant. So we just do the same game again. So we're going over at 0, then we start going up at 45 degrees per decade, and we do this for 2 decades. But this one starts going down for 45 degrees per decade for 2 decades, 1 decade later. So this and that will cancel. All right, so that's why we go across level. Now we have this one going for 1 decade at minus 45, and this one's losing for 2 decades at minus 90. So 45 and 90, that's 135 degrees. Okay? And that's what we have. So here we were at 45 where they leveled off. And so we're going to lose 45 due to this one and 90 due to this piece. That takes us to minus 90. So here we had a slope in here of minus 135 degrees per decade. Here was plus 45 degrees per decade. Obviously that's flat. Now, after 2 decades here, this minus 45 rate stops, and we're just left with this one to lose 90. So for this decade, from 100 to 1,000, we drop by minus 90 degrees. And so now we're at minus 180. And does that make sense? Well, let's see. This has no phase effect. This is plus 90, minus 90. They cancel, minus 180. We line up at minus 180, all done, and this is in good shape. Now, so to finish this, what are our observations? For every power of s in the numerator, there is a shift of plus 90 degrees of phase and a gain slope of 20 dB per decade for sufficiently high frequency. All right? For every power of s in the denominator, there's a minus 90 degree shift in phase and a gain slope of minus 20 dB per decade. And these things simply add up. As you have more s's, they're just get multiples of these. And that's how we do straight line approximations and how we can understand the effects of s in general when we see them in a transfer function, what those things are causing. Now, going back to this picture just for a moment, all right? This is a straight line approximation. If you actually plotted it out, it'll be reasonably accurate outside of the resonance zone, which would be right around 100 radians per second. But here's the point. Well, we can actually use this same system, same kind of approach on machines. So for example, we heard how we would hit machines with sledgehammers and measure the response. That would give us an impulse response, and then we could, using that, we could actually fit models of transfer functions, differential equations, all of those things from that. All right. You can do the same thing here. So picture you go to a machine and you apply many different frequencies and you get the output, and then you get the magnitude and phase. You can generate this off of a machine, and actually you can do it unbelievably easy. For example, we did some of the modeling at GM this way, except there's a twist. Have you ever heard of the concept of pink noise or white noise? Okay, white noise has all frequencies uniformly. Pink noise is adjusted for audio issues. But what we would do is we could actually go to a machine and have a white noise generator that was driving a shaker that would be pushing, picture kind of pushing the metal, as it were, on the locomotive on some given part. And so it will be applying essentially all frequencies that we could then instrument. And we could, by doing long periods of time, so we allowed all these frequencies to happen and add up, we could generate this directly off of our computers and whatnot as they took all the data and handled this. So we would do this in audio using pink noise, which is something I'm not going to go into here, the difference between them, but it's a random noise generator that has contributions from various regions of frequencies. And that would allow us to make these Bode plots. And here's the thing, then it's a really straightforward matter to have a computer to go look at these lines and fit we could say, okay, fit a 10th up to 10th order system to that, and it could fit it really tight. And now we have a heuristic differential equation or transfer function that fit our machine, and they worked really well with the control systems and all of that. So again, we didn't do this stuff by hand. This was something you came up with by hand, then we took it to here. What we would do is we go to the machine, we take data, and then we go backwards to come up with what is a reasonable transfer function, and then we could look at all the poles and the zeros and look at how they're all interplaying and look at damping and natural frequency and all of that good stuff. It was done heuristically. So anyway, that's today's lesson. We have one more part to finish up in our Laplace and systems math side of the course before we start modeling actual systems. I'll see you next time.